All right, welcome to The Explainer. Today, we're going to tackle something really cool. We're bridging this huge gap between the super abstract world of pure math and the down-to-earth, high-performance world of AI code.
So, here's the big question, right? Can we actually take these beautiful, abstract mathematical ideas and use them to guarantee that the AI code we write actually works the way we think it does? Let's dive in.
Okay, so here's how we're going to break this down. First, we'll look at the classic problem of theory versus reality. Then, we'll see how to rewrite the rules for JAX, turn those abstract ideas into real code, build some actual neural networks with them, and finally, look at why this whole thing is so important for the future of AI.
So let's start at the beginning, with this classic showdown. On one side, you've got the elegant, super flexible world of category theory, and on the other side, you have the very strict, very picky, but incredibly powerful compiler, Google's JAX framework.
You see, in theory land, everything's easy, right? You can use simple recursion, you can have objects with all sorts of hidden states, but JAX plays by a different set of rules to get that blazing speed. It needs what are called pure functions, functions that give you the exact same output for the same input, every single time with zero side effects. It has to be able to see inside every single object, and it throws regular recursion out the window for its own super optimized tool jax.lax.scan.
So the big question is, how on earth do you get these two worlds to communicate? Well, the answer isn't to just give up on the math. No way. The trick is to create a kind of translation layer. Think of it like a Rosetta Stone that lets us express these deep mathematical concepts in a language JAX can not only understand, but also optimize like crazy.
And that Rosetta Stone is built on 4 key principles. You could almost think of them as commandments. First, your objects have to be traceable. JAX needs to see all their guts, no secrets. Second, you gotta ditch recursion and use JAX's scan instead. Third, your operations need to be defined as what are called explicit folds, basically a very structured way to process a sequence. And finally, number 4, your core functions have to be pure, so they're predictable. You get these 4 things right, and suddenly your elegant math just works inside JAX.
Okay, theory time is over. Let's see how these rules actually work in the real world. We're going to take 2 fundamental concepts from category theory, algebras and homomorphisms, and watch them transform from these lofty abstract ideas into concrete JAX-ready code. First up, the F-algebra. And yeah, I know, the name sounds a little intimidating, but don't worry about it. Just think of it as a recipe. It's a simple blueprint for taking some complicated structure, say a long list of numbers, and collapsing it down into a single, simple result, like finding their total sum.
And boom, here's what that recipe looks like as code. It's a simple, traceable data class. See? No hidden corners, no secret rooms. JAX can see everything. The struct map, that's the part of the recipe that does the actual work, and any params it needs. It is all laid out in the open, which is exactly what a picky compiler like JAX wants to see.
Okay, next up is the homomorphism. Now, if an algebra is a recipe, then a homomorphism is like a super reliable translator between 2 different recipes. It's a special kind of function that acts as a guarantee, promising that the core structure of your data won't get lost in translation as you move it from one system to another. And this equation right here, this is the heart of that guarantee. Now, I know it looks a little scary, but the idea behind it is actually pretty simple. All it's saying is this: it doesn't matter which order you do things in. You can collapse your structure first and then translate the result, or you can translate all the individual pieces first and then collapse them. If you have a true homomorphism, you are guaranteed to get the exact same answer both ways. This is our mathematical safety net.
All right, now for the really cool part. We can take these well-behaved, mathematically proven building blocks and start constructing actual, real-world neural networks. We're talking about building components that are correct by design.
Let's take a recurrent neural network, an RNN. From a mathematical point of view, an RNN is really just a fold. And a great way to think about a fold is like rolling a snowball down a hill, right? It processes a list of things one by one, and at each step it picks up a little more information, carrying its state, that growing snowball, forward to the next step.
And here it is, that beautiful, simple idea made real. This is a principled scanRNN module, and that one line of code using jax.lax.scan, that is the snowball rolling down the hill. It perfectly captures that pattern of a fold, but in a way that JAX can understand, compile, and run at lightning speed on a GPU.
And just look at the payoff here. We really do get the best of all worlds. The code is totally JAX compatible, which means it's super fast. It's mathematically sound because its structure is a direct mirror of that categorical definition. But here's the kicker. It's verifiable. We can actually write tests to prove it follows the laws of mathematics.
And that brings us to what might be the most powerful part of this entire approach: verification. We don't have to just cross our fingers and hope our code is correct. We can write tests that mathematically prove it.
So how do we do that? We use this really clever technique called property-based testing. Now, instead of checking just a few examples, like does 2 + 2 = 4, we check the fundamental laws themselves. We're not asking, does this work for the number 5? We're asking, does this code obey the law of commutativity for any possible number you could throw at it?
And this is what makes it so revolutionary. When a test fails, it doesn't just give you some cryptic message like wrong answer. It gives you an error that looks like this. It tells you precisely which mathematical law your code just broke. Think about that. Your bug report is literally a failed mathematical proof.
Okay, so let's zoom out. What's the big picture here? After all this work translating abstract math into picky JAX code, what's the real takeaway? Why does this matter for the future of AI?
Well, what we've seen is a complete system for building AI components. By making sure our code is JAX safe, that it's built on these pure functions and that it's verifiably correct, we get this incredible guarantee. The code we write actually does what the math says it should do, and that leads to models that are way more reliable and trustworthy.
And this leaves us with a final, pretty powerful thought to chew on. What if every single component in our AI systems came with its own mathematical proof of correctness? This whole approach points toward a future where we can build AI that's more reliable, more robust, and just plain more trustworthy. Not by just testing it more at the end, but by designing it with mathematical correctness baked in from the very first line of code.